Continuing in our discussion of integrals of vector functions, we previously used the indefinite integral for vectors as well as the definite integral for vectors rules in the video which preceded this. So that basically brings us to our fundamental theorem of calculus application for continuous vector functions, which looks pretty similar to what we saw in Calc 1, we just have applied this vector notation to it. Okay, so it's just the same. Notice that any antiderivative of a vector function is also a vector function. So this produces a vector function, meaning we will still have t's in our result. However, the definite integral produces a single constant vector. And if you go back and you look at the two examples we did in the first video, you'll notice that the indefinite integral still had a t in it when we were done, whereas the definite integral had constants as the coefficients of I, j, and k. All right, so let's work on an application problem. For this example, we're going to deal with knowing the acceleration vector. So suppose we don't know the path of a hang glider and we only know its acceleration vector, a of t. Given an initial value at t equals 0, the glider departs from a point 4, 0, 0. And that point 4, 0, 0, that gives us our initial position. And if you think about where that point is located in 3 space, that is actually an x-intercept. So given an initial value at t equals 0, the glider departed from this point, 4, 0, 0, with an initial velocity. Let's find the glider's position as a function of time t. So first, we're presented with our acceleration function, negative 3 cosine ti minus 3 sine tj plus 2k. And an initial velocity, the velocity at t equals 0, is given by the vector 3j. So let's find position as a function of time. So we're given acceleration and we're going to want to find that position vector. Well, what you should remember from Calc 1 and Calc 2 is that the derivative of position gives us velocity, the derivative of velocity gives us acceleration, and working backwards, the antiderivative of acceleration gives us velocity, and the antiderivative of velocity gives us position. So let's work through this problem. Our goal here is to find the position vector, r of t. And we need to think about what we know. So we know our acceleration vector, and that the acceleration vector is the second derivative of position. We are given initial velocity, and we're given the initial position. So we can write that our vector at time t would be 4i plus 0j plus 0k, or rather r of 0 is 4 times the I vector. So in order for us to find velocity, the first thing we're going to do is to take that antiderivative of acceleration. So the integral of the acceleration vector is going to give us the velocity vector. So that's going to be the integral of negative 3 cosine ti minus 3 sine tj plus 2k k integrated with respect to t. So the integral of 3 cosine t, we're going to have negative 3 sine of ti. The integral of 3 sine t, that's going to be negative 3 cosine t. So I've got plus 3 cosine tj. And then the integral of 2 is going to give me 2t k. Of course, we have plus some constant since this is an indefinite integral, c sub 1. Don't need that parenthesis there. What we have here represents our velocity vector v of t. And at this point, we can use our initial velocity to determine what that c value is. So we are going to use the fact that v of 0 equals 3 times the vector j to find c sub 1. So if I plug in 0 for t, I know that that vector 3j will equal negative 3 sine of 0 times the vector I plus 3 cosine of 0 times the vector j plus 2 times 0 times the vector k plus c sub 1. Now we know that sine of 0 zeroes out and 2 times 0 zeroes out. So this simplifies to 3 times j equals 3. Cosine of 0 is 1, so equals 3 times the vector j plus c sub 1. Now, if I subtract that, I have 0j equals c sub 1. So c sub 1 in this situation equals 0, which is nice, convenient, and easy. So my velocity vector, v of t, is negative 3 sine of t I plus 3 cosine of t j plus 2t k. And I don't need to write plus 0. So there's no constant on our velocity function, which is convenient. So we have our velocity function. We solved that initial value problem to find what our arbitrary constant would be. We still are working towards the position function. In order for us to find that position function, we're going to do the same thing, but then we will use this initial condition to help us determine our next c value. So coming back down here, one thing that we know is that the integral of the velocity function is going to give us our position function. So I need to integrate negative 3 sine of t I plus 3 cosine of t j plus 2t k. I need to integrate that with respect to t. So my position function r of t, the integral of negative 3 sine t, is going to be positive 3 cosine t I. The integral of 3 cosine t is going to be positive 3 sine t j. And then the integral of 2t is going to become t squared k plus another arbitrary constant. In this case, we'll call it c sub 2. So again, as I already said, we know an initial condition. R of 0 equals 4i. So we'll set that up. That means 4i equals, I'm going to plug in 0 for all of my t's, 3 cosine of 0 I plus 3 sine of 0 j plus 0 squared k plus c sub 2. Cosine of 0 is 1, so I have, let's see, 4i equals 1. So cosine of 0 is 1 times 3. I have 3 times the vector I plus sine of 0 is 0. So I've got 0j plus 0k plus c sub 2. Simplifying what we have here, those are gone. Subtract that 3 over. I have that I, 1i, equals c sub 2. So my position vector, r of t, is 3 cosine t I plus 3 sine of t j plus t squared k plus c sub 2, and c sub 2 we just found was equal to I. I've run out of space here, so in order for me to clean this up, I can't scroll down anymore. I'm going to erase some of what we have done. My r of t function, if I want to simplify this, you'll notice I've got two I values. I'm going to combine those coefficients. So I have 1 plus 3 cosine t I plus 3 sine of tj plus t squared k. So I've solved an initial value problem using vector functions, and I found my position. So we started with acceleration, did the antiderivative, solved an initial value problem to find the exact velocity function, and similarly with velocity, we took the antiderivative, found the integral, solved the initial value problem, found our position function. And for the last little bit here, I've brought in this coil around the z-axis. This represents the path of our hang glider at time t. So starting at our initial position, zooming around the z-axis. And pay special attention, this is not specifically a helix. It looks like a helix. However, because that vertical change is increasing more rapidly, it's not staying at a constant vertical change, we don't call it a helix. All right, so I hope that helps you guys understand what's going on with integration and vector valued functions.